Hey there. So for today's little question, it was pretty much in short, how do we know that the stars, which are very, very far away from us and we can't get to because they're super, super hot, how do we actually know they are made out of some gaseous atomic elements and not cheese or, I don't know, like wood? I guess wood would do this too, but maybe not cheese. There are a few ways we do this. One, which we're not going to talk about really, has to do with the fact that if they're made out of something that burns like wood, the burn time of the stars would be very, very fast and it wouldn't go with a lot of other measurements. The only thing we can actually get to burn for a long time that we see is easily fusionable hydrogen and helium and etc., heavier and heavier elements. But the other way we do it is with atomic spectrographs. We are talking today about the Rydberg equation, which states that 1 over lambda equals this Rydberg constant R times, and then 1 over n minus 1 over n, and these are squared quantities, where this is some final position, and this is the initial position it kind of starts with, where we're going from some high energy down to a low energy so that some photon is kicked off of the star, and that's the starlight. What we actually do in order to check out like what the stars are made of is we will take that starlight which is coming in. So imagine that we have some starlight, and the issue with the starlight is it's non-coherent. The light always isn't in the same position of its wave function. So we need a way to make that coherent. A common way to do that is if we take a single slit. The non-coherent light, when it passes through this, will become coherent. And once we have this coherent light, now we just need a way to cause the light to interfere with itself. A easy way to do that is with a double slit. And if we have a double slit now and some viewing screen, then what we can say is, hey, look, like we are going to have some sort of central peak, and then, oh, that's poorly drawn. And then our fringes. Oh, that is so poorly drawn. Right? Oh boy. Ugh. Yeah, you get the idea. We talked about this in wave optics. When wave optics we did this, we only had green light for our green lasers in class. So we only saw, very specific points. We saw like the bright green fringe, and then we saw like our next fringe, and then our next fringe. And I think for our CD lab, we actually had one more fringe kind of out further, and then symmetry on the other side with our points, and the next one would be like down further. We only saw green because we only had green light. For our stars, they're not burning just green light, and they're not burning just blue light. They are burning on some sort of black body radiation curve, which we also talked about in wave optics. And on these black body curves, we kind of have, a spread of light that exists here. Because of this spread, we'll see kind of peaks in different things. But what we can look at in terms of what these points are on the interference curve is that for something like spectral hydrogen, we're going to have what's known as an H alpha line, which is this like nice bright red line here. And then we're going to have kind of like two blue lines here, and then there's kind of like another line. Where do I want to draw it? Like right about there. These are our spectral lines, and these are the spectral lines that are emitted by hydrogen whenever hydrogen is burning in its very specific way. Whenever we have the hydrogen decrease due to its atomic energy levels, specifically like this is an energy level, this is an energy level, this is an energy level, and I guess we have one more here. And this is our common energy levels. And because hydrogen is dropping like this, we see these specific points right here. And only hydrogen will ever make that pattern. So you can kind of ID what element is burning just by taking an atomic spectra of it with a double slit to kind of break up all that light into its component parts. If you did this for helium, you'd have a different setup. I believe helium actually has like a very strong kind of like orangish line here. If I'm right, I could be wrong on that though. Maybe that's the sodium line that is like that. But basically you take all your different elements, and whenever you burn them, and they run through this kind of jump down here and kick out their photons, we will see very specific patterns that are created for them. And it gives us an idea of exactly what the stars are made of because of that. What gets a little janky for astronomers is that you'll get a bunch of these lines like kind of overlapping each other from different elements, because stars can be burning hydrogen, helium, lithiums, oxygens, carbons. They can be burning a bunch of things, but you kind of pass it through a computer algorithm to kind of sort everything out, or even just place filters in front of your telescope so that only the hydrogen's coming through and then only the helium's coming through, because you know what it needs to look like, so you can do that. So that's how we kind of set that up. Another neat thing about this is if you know what kind of light that is burning, or what kind of gas is burning and emitting its light rather, you know just based off the Rydberg equation for hydrogen, and that equation really works well for hydrogen. It doesn't work super great for anything else. You know where this line should be. But let's say this line pops up over here, and then all of a sudden it pops up over here maybe a month later. And then, 2 weeks later it pops up where it should be, and then 2 weeks later it's over here. The line is moving back and forth. Well, what that tells you is that the star, we'll put the star here in red, the star is actually moving. If your eye is down here, then what this tells you is that this light of the star is coming at you at some times, and then at sometimes the light from the star, well, the star itself is moving away from you. So the star is moving towards you here, the star is moving away from you here. It's moving like in a circle, like this. So this light coming towards you is blue shifted, and the light as the star moves away from you is red shifted. If you know, based off of your spectrograph, how long it takes to go between these two different max and mins right here, such as this point and this point, how long does it take to go back and forth? That tells you what the orbital period is of the star. And what's really cool if you go back to mechanics is that if you have a two-body system, body 1 and body 2, even if this first body is much more massive so that its orbit is much smaller, these objects, if they're just kind of orbiting each other, or the barycenter, the center of mass here, they will always be opposite on it. So if this is going around the center of mass like this, and this is making a much bigger arc like that, then whenever this large piece is down here, this piece will be up here. They'll always be opposite and through that center of mass, which means that both of these have the same period. And what's cool about this is if you know the period of the star, that means the period of the star has to be equal the period of whatever's orbiting around it, assuming there's only one body, which means that's the period of the nearby planet. And if you know the period of the planet squared, you know this is equal to 4 pi squared semi-major axis cubed over g, universal gravitational constant, and then the mass of the system, which normally we just call this the mass of the star because the planet's so much less than the mass of the system. But what this tells you, and I'm getting super excited about this, is that if you know the period of the planet, then you know how far away the planet is from the star, and if you know how far away the planet is from the star, and you know what type of star it is and how hot it burns, you can get an idea of if that planet is habitable or not, and could there be life there based on the habitability. So just this one tiny thing back here, understanding the double slit and saying, hey, look, I know what light's coming in, that tells you a whole lot more using what's known as the radial velocity method of planetary detection. So kind of a neat thing there. It all stems from just light and understanding what the Bohr atomic model of hydrogen is doing. So that's kind of interesting. Kind of a crazy little quiz question, but hope you enjoyed it, hope you thought about it. And that's kind of what we're looking at there to extend beyond just this simple concept in the classroom. So take it easy.